Hi everybody, welcome back to more probability. And today we're going to cover a variety of topics. These are a little bit more challenging than the problems that we've done in the past. So we're going to cover symbolic notation and some of the formulas that you'll see with probability problems, as well as finding probability given probability, what we sometimes call working backwards, and then some challenge problems, including creating Venn diagrams and doing at least one problems and things of that nature. You can print out the notes and the example problems that go along with this video and follow along so that you'll have those as a reference. In probability, we use what we call set notation as symbolic notation, and you'll see this used a lot on SAT or ACT problems, so it's good to recognize what these mean. We've talked already about what the OR problems are and the AND problems. So remember, OR means union and AND means intersection. And so if you can remember that OR means union, that's an easy way to remember what symbol goes along with the problems for probability, because this U looking symbol means union. So what this is showing here is the probability of A or B, or A union B. Next we have the AND problems, which as you recall means intersection. And if you look at the N in AND, that kind of looks like this little guy over here, which is kind of an upside down U, but it looks like an N, and that means intersection. So this is the probability of A and B. And then something we haven't talked about yet is what we call the complement of an event. The complement means that it's anything but, in this case, event A. So a complement is denoted with either one of these single little quotation marks, or you'll see a bar over the top, which is less common, but it does show up on some standardized tests. And then more frequently, you'll see a little exponent that looks like a C, which means complement. So if you recall that all the probability, all the possible options add up to 100% or 1. So the complement of an event would just be 1 minus the probability of the event happening. Probability formulas are usually written with the set notation, and they look a little bit confusing until you understand what the symbols mean. But once you understand what the symbols mean, it's pretty straightforward. So in our prior examples on different lessons, we had talked about OR and AND problems. And you'll recall that for the OR problem, we were talking about the probability of event A or event B happening. And so we counted everyone up. It's a union problem. So we took the union of both events. So you'll see in the formula here, it's showing that we have the probability of event A. In this case, say it's passing classes. And then the probability of event B, and then we have to subtract the probability of events A and B. That's not to say that we're not counting them at all. We just can't double count them. And as you can see in the table here, if we don't subtract that 85 who are passing and will attend, if we're working with our totals, we would double count those. So when you do your calculation, you would have the probability that they attend, which is 96 out of 144, plus the probability that they are passing classes, 100 out of 144, and then subtract where they overlap. Subtract that 85 out of 144, because we've counted that 85 in both groups already. And so we would get 111 out of 144, which is the same as if we had added those three numbers up in the table, which is how we did the problem initially. And so our overall probability of A or B would be 0.77. Similarly, if we refer to the example we did before with the AND problem, we're saying that we're taking the probability of A and multiplying it by the probability of B, the second event, given that the first event has already happened. So we have to use our conditional probability here. So if we look at our table again, the probability of both events passing and will attend would be 85 out of 144. So if we do that with the formula, we would have 96 out of 144 who are passing, who will attend, and then 85 out of 96 are passing given that they will attend. So that's our conditional probability that we're working with. And so our overall probability for events A and B, passing and attend, is 85 out of 144, or about 0.59. And then the conditional probability looks confusing, but look, it's just this and formula rearranged. So if I rearrange the variables, up above we have the probability of A times the probability of B given A is equal to and probability A and B. Now I've just rearranged that formula to solve for the conditional probability. And so usually you see these three highlighted formulas on a formula sheet, but do know that if you're ever given a problem where they say events A and B are independent, then remember you're still using this conditional probability formula, but recall that if the two events are independent, then the probability of the second event, B, is going to be equal to the probability of B given A. So that was one of our definitions of independence. So really you're using the same formula. It's just that in the problem, if they give you that the two events are independent, you can just multiply the total probabilities. So let's try these examples. So the first example, you want to use your formulas that we just went over. And given the following, the probability of event A happening is 0.8, event B is 0.46, and the probability of events A and B together are 0.28, find the following. So I'll give you a few minutes to think about these and use your formulas and see if you can plug in the numbers and get the correct probabilities. Okay, so for part A, you want to plug in the probabilities for A and B, and then A and B. So you have 0.8 plus 0.46, and then don't forget to subtract A and B. So 0.28. So you should get 0.98 as your answer for A. On part B, you're asked for the conditional probability of B given A. So on these problems, students often wonder which probability they need to divide by in the formula. So if you notice this is B given A, then that is what tells me what I need to divide by over here. So I'm going to have probability of A and B divided by the probability of A will give me the probability of event B given that event A already happened. And then lastly, in part C, we're asked for the complement of B. So that means not B. So I just take 1 minus the probability of B to get the probability of not B, which would be 0.54. Okay, so our next example problem. In this problem, it's a little bit different because you're given the probability of A is 0.48 and the probability of B is 0.25, but we're also told here that the events are independent. So that means I can use these two probabilities to figure out the probability of A and B by just multiplying these two together. So look at these A, B, and C and see if you can figure those out. So I kind of gave the first one away, didn't I? So the probability of A and B part A. Just multiply those together and we get 0.12. So now part B, the probability of A or B, well, independent does not mean that they're mutually exclusive or disjoint events. As a matter of fact, we know from part A that if we multiply these two events together, the probability of these events together, we get 0.12. So in fact, if two events are independent, they cannot be mutually exclusive. So remember, in part B, we need to subtract the and. We need to subtract the answer we got in part A in order to get the probability of A or B, which is 0.61. And then lastly, it's asking for the complement of A and B. So if you think about this, you want everything that is not A and B. So we want to subtract 1 minus 0.12 to get 0.88 for the probability of not A and B. Okay, so on to example 3. Now this is a little bit more complicated, and these are the kind of problems that people start running away from when they talk about probability. So bear with me, we're going to walk through it step by step, and I think if you take the time to do this problem, you will see that they're really not that hard, and you can approach all of these problems in exactly the same way every single time, and it will work. So example number 3 is what we call finding probabilities given probabilities, or sometimes working backwards. So here's our problem. This season, the probability that the Braves will win a game is 0.64, and the probability that the Braves will score 5 or more runs in a game is 0.52. The probability that the Braves will win and score 5 or more runs is 0.46. What is the probability that the Braves would score 5 or more runs when they lose the game? Round your answer to the nearest thousandth. So lots of words on the page, lots of numbers on the page. If you want, pause the video, see if you can solve this on your own. And if not, just keep going and we'll solve it all together. Okay, so time to get out your highlighter again and highlight the important parts of the problem. So we have two different events. We have event winning a game, and we have an event of scoring 5 or more runs in a game. And so we've highlighted win a game. The probability of winning a game is 0.64, and the probability of our second event, scoring 5 or more runs in a game, is 0.52. And then in green, we've highlighted that the Braves win and score. That's where they intersect. That's a combination of both events, and that probability is 0.46. So the way that I suggest you attack these problems is make yourself a two-way table. So if you make a two-way table with event of win or lose, so they win, not win, and then the second event is that they score 5 or more runs, or they don't score 5 or more runs. Of course, you could write that they score less than 5 runs. Either one of those is fine, but they're always a yes-no situation. And then start to fill out your table. And then keep in mind what the question is asking is for conditional probability when they lose the game. So given that they lose the game. So when is kind of another keyword for given. So given that they lose, what's the probability that they would score 5 or more runs? So when we fill out this table, in this case, they've given us the probabilities, but I think it's a lot easier to work with actual numbers than probabilities. So we don't have a total number of games, just make it up. So obviously, if you're given probabilities like this, it's easy to make your total out of 100 and then fill in your table. So we were told that the probability that they win a game is 64 out of 100, and the probability that they score 5 or more runs is 52 out of 100. So I've entered those in the two total areas. And then the probability that they win and score 5 or more runs is 46 out of 100. So then go ahead and complete the rest of the table just like we did before. It's basically like a Sudoku puzzle. So we can subtract 52 minus 46. That gives us 6 who score 5 or more runs and lose, and so forth. So go ahead and complete your table, and then we can answer the question. So now that we have our table all filled out, let's answer our question. What is the probability that the Braves would score 5 or more runs when they lose the game? So given that they lose, what is the probability that they score 5 or more runs? So remember, now we're looking at conditional probability. So I'm only looking at the column when they lose. So out of the total of 36, I have 6 out of 36. So the probability that they would score more than 5 runs given that they lose is 6 out of 36, or approximately 0.167. So the question had said round to the nearest thousandth, and so that would be our answer. 0.167 would be rounded to the nearest thousandth. Again, so every time you have one of these problems that looks complicated, sketch it out and make a table. Identify the 2 different events you have. So you have events winning, and then the event scoring 5 or more runs. And then the other column or the other row that goes with that category would just be the opposite. So win and lose. Score 5 or more runs, doesn't score 5 or more runs. It's always a yes-no situation. And I think if you find that and then you convert your probabilities to actual numbers and work with numbers, the problem is much easier to work with and to solve. So on to example number 4. So in our example, we're going back to our jar of marbles. So our jar of marbles contains 14 red marbles, 8 green marbles, and 12 blue marbles. Part A, select 3 marbles, replacing the marble each time. What is the probability that at least 1 marble is red? So probability problems, a lot of times you'll see these at least 1 problems. And when you're doing that, you could list out every possible combination. You could get 1 red marble on the first draw, but none after that. You could get 1 red marble on the first and the second, but not on the third, or you could get all 3 red marbles. Well, that's possible. You can do it that way, and you can list out all those different probabilities and then add them up. But I wanted to give you a little hint. If you see a problem that is asking you for at least 1, think about that. The probability of at least 1, the opposite of that, if you will, is the probability of none. So we can use the complement here. So if I can find the probability of getting no red marbles, then I can subtract that probability from 1 to get my at least 1 red marble probability. So it sounds complicated, but it's really not. So anytime you see at least 1, I want at least 1 red marble. So let's find the probability of selecting 1 red marble that is not red. So if you recall from this problem, we need to add up add up all of the marbles to get 34. We have 14 red marbles, which means we have 20 that are not red. And so that's just 1 red marble, or 1 marble that's drawn from the bag. But in this case, I'm going to draw a marble, replace it, draw another marble, replace it, draw another marble, and then I have my 3 marbles. So if I want to find the probability that none of them are red, then I can take this probability of 20 over 34 and multiply it by itself 3 times, or 20 over 34 raised to the 3rd power, and I get 0.2035. That would be the probability that in all 3 draws, none of them are red. And so to get the probability that at least 1 of them is red, just subtract 0.2035 from 1. And so I get approximately 0.8. So how would we do this problem if we don't replace the marbles each time? Well, you're still going to do the same basic approach. You want to find the probability that none of the marbles are red, but remember you have to work with conditional probability, and you're going to have to adjust the probability for each time you draw a marble out of the jar. So in this case, if we are not replacing the marbles, the first time that we draw a marble that is not red, it would be 20 out of 34. The second marble we get would be 19 out of 33, and the third marble would be 18 out of 32. And then we can multiply those three probabilities together to get approximately 0.1905. And then we subtract 0.1905 from 1, and we get approximately 0.81. So you can see that the probability here is a little bit higher than if we did replace them every single time, because the probability of there are fewer and fewer not red marbles left in the jar every time that we select one. So the probability is so close in this case if we rounded to the nearest tenth, but if we took it out to several decimal points, or if we had a lot more marbles in the jar to begin with, we would see a much bigger difference. Just a reminder here to remember that when you're doing these problems with selecting 3 marbles from the jar without replacement, remember you are always going to get what you want. You always get what you want in probability. So we always get a not red marble in this case, and then we get another not red marble, and then we get another not red marble. And so we can multiply those together and then subtract from 1 to get our final probability. Okay, and then the last example problem that we're going to do today, sometimes they'll ask you to model your probability with a table or a Venn diagram. As I've suggested in the prior videos, I really think it's easiest to work with a two-way table when you're trying to solve probability problems, but you should know what a Venn diagram looks like, and also how to set up a Venn diagram and how to work with a Venn diagram, as well as how that compares to what it will look like in a table. So let's look at this problem. So we have a nice group of 100 students. That always makes it kind of easy. So nice, easy number. 100 students. We have 50 of them play sports. 60 of them participate in a music class. There are 25 students who do both. Create a two-way table and a Venn diagram to model the situation. So in the two-way table, let's start there. So with the two-way table, when we would set up our table, we've done this a lot, so I won't spend too much time on it, but we have our two events. We have play sports and take music. So play sports or don't play sports, take music, don't take music, and then we have 100 students total. So in this problem, we have 50 of them play sports. So we had entered our 50 in the play sports total column. And we have 60 participate in music. So 60 total out of 100 take music. And then there are 25 who do both. So 25 is, we usually show that as a green, so I'll make that green here. That's our and. They do both. And then we've talked about how you fill in the rest of the table just by subtracting. So 60 minus 25, we get 35 who don't play a sport and take music. We get 100 minus 50 who don't play sports at all, and so on. So we can set up our table. So now when we're setting up a Venn diagram, we want to do something similar with that. So we're going to have 2 circles in our Venn diagram. Our Venn diagram is going to graphically depict the combination of students who play sports and or music or none at all. So when you make your Venn diagram, you have 2 overlapping circles. And when you're working with a Venn diagram, you want to start with the and, start with the both. So in this case, this 25 were the ones who play both a sport and take a music class. So put 25 right in the middle. That's the intersection. And then from there, we need to figure out what goes in the outside parts of the circle. So the parts over here where we have play a sport and on the outside of this circle, that would be the students who play a sport who don't take music. And likewise, the part over here where we have the music part of the circle, this would be the group of students that play music or take a music class but do not play a sport. So if you can figure that out, what we have to do is take the total who play your sport, so we have 50 total who play the sport, and subtract out the 25 that we've already counted in the middle here. And then we also have 60 students who take music. I should have made that blue up here probably, but there we go, blue. So we have 60 students total who take music, and so we have to subtract out the 25 of them who we've already counted for here who take music and play a sport. So together, these are going to add up to the total of 60. And then last thing you want to do is go back and make sure that all of your numbers add up to your total. So we were given that we have 100 students in total were surveyed. And so if I add these three numbers up, 25 plus 25 plus 35, that doesn't add up to 100. I'm missing some people. Well, the people that I'm missing are the 15, these guys over here, who don't play a sport and they don't take a music class. And so for a Venn diagram, what we do with them is we write them in a little box off to the side down here. So we just have to account for them somehow. So this would be the group of people that don't play a sport and also don't take a music class. And now together, if we add up all four numbers, 25 and 25 and 35 plus 15, now we have our total of 100 students. So that's how we would model the situation using a Venn diagram and a two-way table, and hopefully you can see how these things would work together. So you can use a Venn diagram to calculate, say, conditional probability. If you wanted, you could figure out, well, okay, so what's the probability, given that a person doesn't play a sport, that they take music? So that's pretty easy to do with a two-way table. Given that they don't play a sport, what's the probability that they take music? That would be in this column right here, right? So we would just use this column and say 35 out of 50. Well, if we're working with a Venn diagram, it's a little bit harder to see that because I want to do the probability that they take music given that they don't play a sport. So don't play a sport would be everything that's outside of the sports circle. So again, I'd have to add these numbers up, and of course they're the same numbers because I'm working with the same data, but 35 plus 15, so our conditional probability would be 35 out of 35 plus 15, which is 50. So I get the same answer. I just think it's a little bit easier to see it in a two-way table than it is in a Venn diagram. But you can use whichever one makes you happy and whichever one you find most helpful. Thanks for joining and have a great day. Bye-bye.